I guess let's get started. So welcome back to our all training sessions. Today we have a training session provided by William Eustace, who is going to talk about data loaders in PyTorch and TensorFlow. William has a lot of experience writing data loaders for very sort of specialized projects. And so he already presented this tutorial last year, which was very popular and kind of gave insights into how to build these data loaders. And so we are very happy to have him back this semester as well to, to give us a next version of this tutorial. So William, please take it from here.
Awesome. Howdy, folks. I guess as I was introduced, my name's William. I guess I'll give another short introduction, which is I'm currently finishing up my undergrad here at the U of I in computer engineering. My focus is in sort of computer vision and hardware accelerators, and I currently work with NCSA, and I'm doing my senior thesis with Professor Kiddertanko. But okay, enough for that. Let's talk about what we'll be discussing today. So as we sort of briefly mentioned, the major focus today is on data loaders. And so we'll first just introduce at a high level, really what are data loaders. It won't be too surprising that the name sort of gives it away. We'll talk about why data loaders matter, more importantly, sort of how we can use them in order to forget that they exist and to make our training go as fast as possible. We'll analyze a little bit on how we can actually interact with them. And then, of course, a big part of this is also the data sets. So, a lot of the times we'll have to create our own data sets when it comes to actually implementing these models. So, very quickly, what are data loaders? So when we discuss data loaders, often we're also sort of referring to data sets, but in PyTorch, at least, and in TensorFlow as well, data loaders at the end of the day are just taking some piece of data and getting it to the graphics card, usually as fast as possible. Every once in a while, we need to sort of perform some augmentation on some data before it gets to the graphics card. But at the end of the day, we want to move the data to wherever we want to perform our compute. And often this loading of the data is a major bottleneck to the model. So if we take the same exact training script and only change this one data loader parameter, the batch size, the difference in times is really astounding, 3 minutes versus 19 seconds. But okay, sometimes changing the batch size is like a little bit cheating since that changes training parameters as well. But of course, we can also look at one where we just change things like the number of workers and pinning the memory so that it's faster to transfer to the GPU. And this, again, can cut our sort of training time down by a half, which is really quite nice. Not many other things, I think, can have such an impact on our training speed. And of course, if we can train it twice as fast, then hopefully we can train a much better model in the same amount of time, is the hope. Okay, when it comes to actually using these data loaders and interacting with them, you can get almost all of your performance gain by doing very little work, which is nice. Unfortunately, on the other side of that, getting any more performance gain out of that sort of gets a little bit harder the more you want, or maybe a lot harder the more you want. Whether it be in terms of physically having to write a lot of code to improve it, or having a large cost of memory, or having a large cost of system drive space. Sometimes these to get an extra 2 or 5% can be a little bit expensive. So, the most simple sort of things that we can do that we'll look at in just a moment is tuning the hyperparameters of your data loader. What's your batch size? How many workers do you have loading that data? Things like this. But of course, we can do more advanced things. So I'll work with images a lot in this example, since I think images sort of run into this issue very often, right? Images are a lot of data that we need to move very quickly to and from sort of the graphics card. So, when we're loading these images, at first from our storage medium, SSD, hard drive, there's usually a lot of things that we need to do to these images before we can give it to the graphics card to process for our model, right? So often we normalize these models, we convert these models to, different data types. Maybe the original image is in, ints, and now we need it in floats. A lot of those things we can do ahead of time. So, let's do that once, resave the images as, pre-processed. So, subtract the mean, divide by the standard deviation. Let's save them as the right data type, of course, if we're doing that. And then, even saving it as different file formats can be, pretty impactful in terms of training time. So, the JPEG or PNG decode time is going to be slower than something like, binary file decode time or something like that. There's other things as well. So, we need to do some augmentations to these images usually. Sometimes these augmentations are random. So, choosing to rotate it a certain amount or to change the colors a little bit, these, it is sometimes feasible to sort of save 10 different copies of an image with different parameters for these random rotations and color changes, or more, 100. Obviously this starts to eat up your hard drive space pretty quickly, but if you really, really care about performance, you at least won't have to do it on the fly. And then, if you have a lot of RAM, we can load a ton of these images in RAM ahead of time, which can make the transfer to the GPU even faster, which is very nice. So before we move on and start sort of talking about these, let's at a high level analyze what's happening. So the major bottleneck when we're working with data loaders is moving our data from one place to another place, of course, right? And some general rules of thumb that we can use to sort of minimize this is first that we want to store our data as close to our compute as possible. So the VRAM is where we're doing our compute. This is on the GPU. It's very fast, but we need to get it there. And so if we're, starting from a hard drive and potentially, very often we move it first to the RAM and then we move it to the VRAM, this can be pretty expensive and pretty slow. Reading from a hard drive is, a lot slower than reading from RAM. And then moving data from the RAM to the VRAM is also not free. That's sort of expensive as well. And so, little things like, okay, can we store this data ahead of time in some faster medium, right? In a SSD SATA drive or a SSD NVMe drive, or again, as I sort of mentioned, if we have enough RAM, just load it all into RAM. And then we don't sort of have to worry about this, right? Which is very nice. And then two, we want to do some useful compute on our data as soon as possible. Of course, no sooner, but this means, when we're storing our data, convert the data type ahead of time, normalize the data ahead of time, things that you're always going to have to do 100% of the time that are always the same. It's often beneficial to sort of store the images like that. Then when we, load this into our RAM, so often the process here is, we have some file of many, 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 many images in our hard drive. Our CPU is running its own sort of process to preload these images and to get them ready for the GPU, right? And so it'll grab some number of these, whatever your batch size is really, 64, 128, and it can perform some augmentations and while the GPU is doing other things, right? So in the background, the GPU is busy, doing the forward pass for the previous set of images or, calculating gradients or things like this, right? And so during this time, the CPU is getting these images ready, right? This one's being transformed like this one's being transformed like this. And then once they're all ready, and once the GPU is done doing what it's doing, the CPU can start to send all of that data over at once, which is very nice. So, there is some benefit, of course, to working in the CPU. So very often we want to do some of these random transformations on the CPU, things like rotation, changing the color, flipping it horizontally or vertically, right? But not all of the time is that the best case. Occasionally there's cases where these transformations that we're doing are sort of very expensive. And the CPU doing these transformations on, 128 different images is actually slower than the GPU doing its processing, right? We have to remember GPUs are extremely fast at what they do, even if they do have to do a lot more work. And so, occasionally it can be more quick to move some expensive transformations to the GPU. So first we move to the GPU, and then we add a little piece here that has it actually perform some of these transformations. So, you sometimes just have to experiment with these things and analyze your training pipeline. And we'll talk a lot about this in some of the things in just a moment. Okay, and then of course, when we do get it to the GPU, the graphics card, we really only want to do a forward pass. Okay, a backwards pass too, but we want, as soon as the data gets there, to start using it so that we can get new data in there as soon as possible, right? Okay, so quick review at a high level, of course, we have our data sets somewhere in storage. Very often we're writing these data loaders in order to sort of collect and pre-process a small batch of these, right? Usually some power of 2, since that's nice for the GPU, but really probably anything's fine. Okay, once these are all processed and ready, we can send them to the GPU, which ideally is always doing something productive, right? We always want to make sure we're utilizing our GPU. At the same time, we want to make sure that we're not sort of overloading the GPU with a ton of data. So sometimes this can be a little bit of a balancing game, right? If we have, these huge high resolution images, but the model that we're running on the GPU is very small, our utilization of the GPU might look something like this. So, this is the time that we're moving data. And then, because it's very quick to sort of process on some model, that's our sort of useful compute time, right? And so there's a lot of things that we want to do, right? A good data loader is going to minimize this data transfer process as much as possible, right? And it's going to make sure that this compute time, or at least the time that we are doing useful compute, is as much as possible. Okay, so let's sort of really dive deeply into some of the easy ways to analyze these. So we'll look first at PyTorch and then at TensorFlow. In PyTorch, this is sort of the default data loader class that we'll use once we create some data set. And we'll just look sort of briefly at some of these parameters and talk about them. So on the left here, I have some normalized execution times for 2 different machines for just a variety of different batch sizes. This was both on how, I think this was 1 GPU, and this one is 4 GPUs, or I think it was 3. And so, we see some different ranges. This can get up to much higher batch sizes. The execution times are also lower because this has like 60 CPUs all doing the work. Okay, but batch size is the first one. So every time we're loading an image from our storage, how many of these images are we loading at once? At the same time, when we send these images to our graphics card, how many sort of forward passes are we doing at a time? Generally, I think it's good practice to sort of try to max out your batch size. At a certain point, the limiting factor is usually not your maybe, okay, maybe it is system IO in certain cases, but I think in a lot of cases, you'll run out of CUDA memory first. Oh yeah, sorry, I don't have labels on these because I'm a bad scientist, but this is batch size here, and this is we'll say execution time. Okay, so and these are just, again, 2 different machines. So we see, generally speaking, a bigger batch size means lower execution times, right? Of course, happy to help. And so, we say, okay, batch size of 512, this runs at 40% of the time that it would have taken with a batch size of 1, right? In this other machine, it's maybe a little bit more noisy, but generally speaking, there's this downward trend in batch size. Again, though, once you reach a certain point, you'll run out of CUDA memory. And of course, you can't really go past that, right? So, one thing that we can do to speed up training very often is increase batch size. But we have to remember, our computers aren't perfect. If we just try to max out batch size as much as possible, sometimes we can sort of congest the data, right? Because a larger batch size does mean our CPU, is having to use more memory in order to store these images. In the meantime, it has to transfer more data when we're moving it to the GPU, which can take longer. But okay, sometimes it's worth it because we're still looking at more images at the end of the day. Okay, another very sort of valuable one is the number of workers. Okay, briefly, I'll just mention shuffle. This does exactly what you think it does. Every epoch will reshuffle the data set. I had a large bug just 2 days ago where I forgot to turn shuffle to true, and it caused me probably like 3 hours of annoyance on why my model was being very strange. But num workers is another very important one. Very simply, how many processes are we spawning up on the CPU that are all doing this task of loading data, right? So of course, our CPUs have many cores, and on HAL, we're lucky enough to have, 160 possibly, different threads that we can be running, or okay, more threads, but we have 160 cores that we can basically be using on a node. And each of these cores can be doing very valuable work. They can each be reading a different piece of memory. And so, as we increase the number of workers, what do we see? So on a small machine, this machine, I think, had 8 cores or something. We see that 8 is a pretty good number. So, obviously with only 1 worker, we get sort of very large times. As we continue to decrease this, we can speed our training up by, a little bit more than 2 times. And as we continue to go sort of past the number of cores we have, there's some diminishing returns. So for this one, around 8 or maybe 12 is a good number. And so, we can sort of analyze this and use it. As a good rule of thumb, just choose the number of cores that you have. But this isn't always the case. So this second machine here had 80 cores and, it was 160 cores and 3 GPUs. If we have 160 workers, this also means that sort of the IO, the computer's always reading something, right? It has 160 people all trying to read the same thing. And so eventually we start to get not even diminishing returns, but negative returns from adding more workers, even though we have the sort of available cores, right? And so it can be valuable sometimes to just benchmark this, right? Add some timing statements in your code, select a specific number for the number of workers and see how it performs. In this case, it seems like 20 or so was maybe the best number. Oh, I've also forgot to mention these 2 different lines are 2 different versions of the same data set. One is lower resolution, 160 pixels. One is higher resolution, 320 pixels. And, there's maybe some interesting takeaways from this too. We can see that sort of, these diminishing returns with having more workers is a little bit more severe with the higher resolution data, right? Or maybe our benefit is a little bit less. It's another way to say that. Great. Okay. There's other things as well. I'll briefly mention pin memory. This just aligns when a process is loading data into RAM, it'll align it in a certain way so that it's very quick to move to the graphics card. Sometimes if it's not aligned, it can be a little bit slower. Generally, false or true, this can have a little bit of a significant difference. People, preach to say that it should always be true if you're doing compute on a graphics card. In practice, I've usually seen this either has sort of no effect or gives me something like a 2% increase. So, okay, it's probably maybe not that significant of a gain, but I suspect if you have many, many GPUs and you're often, sort of worried about moving data to GPUs, this gain can become much more significant. With 1 GPU, it's usually negligible. With 3 or 4, you start to see a little bit of a gain, and I haven't benchmarked it with any more than that, 8 or 16 or anything. But there's also this prefetch factor that we'll analyze very quickly. So, of course, there's this downtime potentially. We have some core that, okay, this is, it's storing data at this time, the GPU is doing compute at this time, and then once the GPU finishes its compute, we can begin sort of sending this new data to the GPU, right, to process, and then it can begin compute on that. But, we can do some extra work in the downtime. So, okay, we're doing work right here, moving the data, but right here, we can load a second image. So we can load sort of the next batch, right? And so then next time, the GPU is ready, or if a different GPU is ready, we already have this batch ready to send. And so that's what this prefetch factor is, right? This is saying, hey, we'll prefetch up to 2 more examples. So we'll have the main example we're trying to get and 2 others. Now, of course, nothing comes for free. If we increase this prefetch factor to some crazy large number, in certain cases, we actually see that it reduces performance. We can see some general upward slopes, meaning this has higher execution time for a higher value of prefetch factor. And then in this one, it's just sort of very noisy, right? Maybe some slight speed up. But okay, with very large values of prefetch factor, we have to use a lot of memory, right? You have to recall that, the space this is going to take up in memory is the size of your data. times your batch size times your number of workers times your prefetch factor. Okay, and so if each data is only 1 megabyte, but we have a batch size of 512 and we have 60 workers and our prefetch factor is 10, this can very quickly lead to a situation where we run out of system memory, potentially for not that much of a speed up. So okay, if you're doing data loaders in PyTorch, these are some simple adjustments that you can make to really speed your code up. I hope that maybe you have a little bit better of an understanding of these, which can be pretty helpful. We'll also discuss some of these for TensorFlow. So TensorFlow has this nice tf.data API. And this tf.data API has a lot of sort of just chainable calls that we can use. So prefetching, interleaving, mapping, caching, and we can briefly analyze what these will actually have an impact on. So prefetching is relatively simple, right? Just to sort of analyze what's happening here, we open some file, we read our data, and then we send it to the GPU to train. And then while the GPU is training, we can begin reading the next one, right? So prefetching will just sort of enable you to do that, allowing some overlap. So, okay, very easy to implement that. All you really have to do is add a .prefetch. Very often there's some overhead when we attempt to read data. So, when we try to open a file, there may be some large delay if it's on some network drive or something. And so, very simply, this interleave allows us to just make 2 copies, sort of each one smaller. And so if one sample is not ready, the next sample might be ready, right? And again, this can sort of speed up our read time from our data set, which is nice. Okay, and then we can also parallelize these calls. So if we have, n different data sets, nothing is stopping us from saying, okay, let's sort of be reading from multiple of them at the same time. And so just by sort of adding this parameter to this function, we can, have it even auto find out the best number of parallel calls to use here. And so then, we can be reading from multiple data sets in parallel, saving a lot of time, which is quite nice. Of course, everyone's favorite, we do need to still perform sort of augmentations on these images, which we can use this map for. And we can add this to sort of this call graph. We open the file, we read the data, we augment the data in some way, and then we train on that data. We can make sure that we're executing these map calls in parallel as well. There's no reason why one core needs to be doing these, right? We can do these in parallel. And so then whenever one is ready, we can immediately send it to the GPU once the GPU is ready as well, and save a lot of time there. And then also caching, of course, is always available. In this situation, maybe it's a little bit interesting. We can see that they're caching after the map. And so, if you do have sort of random augmentations, you can also cache after the read, which is nice. And then, perform the map on the cache value there, which can be very valuable. So, we can always pre-process our data like this. And this too can be parallelized, right? Now we can get these sort of crazy, tying them all together, parallelizing the map, caching the results, all sorts of very fun stuff. So if you're using TensorFlow, this tf.data API, it's very sort of easy to add all of these. You'll have like some data set. And really all you have to do is say data set, dot map of my function dot cache of the things I want to cache. It's quite easy, which is nice. Okay, but we've made some assumptions here, and one of these primary assumptions is that it's easy to sort of have this data set, right? We have a clearly defined data set, and I think this is true in a lot of cases. I think many of us that are working on sort of these pre-existing data sets like ImageNet, or data sets that we're downloading online, it's quite easy because very often these are in a nice format, and we can use sort of these pre-built data sets in order to just instantly have a sort of this data set class is what we'll call it. But that's not necessarily true. I think a lot of us are sort of working on our own data sets, right? We're out there collecting our own data, and it's maybe not in the best form. and the labels aren't totally clear. And so that's what the rest of this discussion is going to be on, is how can we create our own data sets. And these data sets are super important as well, and they tie into sort of fast training code. These PyTorch versions of data sets and aren't always perfectly efficient, right? At the end of the day, if you choose to convert, ImageNet, for example, stores all of its images as JPEGs, right? Which is, pretty efficient, not the most, quick decode time, but not slow by any means. We could, write our own data loader that instead of reading these JPEG files, one time, we'll save them all as binary files. And now we'll, directly read these binary files, maybe even directly to the GPU, right? To do that, we need to write our own data set. These things don't exist already, right? Because these are sort of more specialized. Or I think the much more common case is we just have our own data set and we need to sort of analyze how we're processing it. Okay, so I do have a Colab/Jupyter Notebook link that I just put in chat. This will be for later. I have it up on my machine too. I think it's just good practice if any of you want to sort of continue to learn how to write your own data sets, but I figured I'd send it now just to let you have access to it. Maybe it's also good to review, but okay. We're going to use this same format that we see here. Technically, this is like the PyTorch format. However, Keras has this same tf.keras.utils.sequence, which is the exact same. And so the only change we would have to make would be this, and then basically just put this here. And then we have a Keras data set as well. Same exact functions, init length, get item, and we'll analyze right now what these parts are. Okay, so in the init function, we sort of do all of the things that we need to do to get our data set set up, right? Sometimes it's not totally clear what this is, but we'll look at some examples in a bit. The length function is maybe sort of obvious. We return the length of our data set. Of course, PyTorch or Keras needs to know, when we iterate for item in, our data loader, it needs to know how big the data loader is, right? And for the data loader to know how big it is, it needs to know how big the data set is, right? And then it's, data set length divided by batch size, basically. And then, of course, maybe the most important of these all is the get item function. So given some index, we want to return some data and its label. So let's look at an example for these. So we have this very common sort of form of images where we have our data set folder, we have a training folder and a validation folder. Within this training folder, we have a lot of subfolders, one for each one of our classes. And then within each of these class folders, we have maybe many images, right? This is the exact same sort of form as this image folder. So technically, we could just use this here, but okay, we want to create our own because we want to learn about this. So sometimes, when we just have our data sitting somewhere, it can be a little bit difficult to figure out how to create a good data loader for it. I think some good questions that I've learned to ask myself is, okay, what is one example from our data set? In this case, it's very easy. One example is one image, right? That one's not hard. How can we represent these in an array? Okay, I can just store maybe an array of all of the paths to the different images. Okay, and then what do we need to do to build this array? Okay, let's see, iterate over the classes, iterate over the files, and then store them in some big list, right? Okay, and so let's try to do this. So I've sort of pseudo-coded it out here, and then we'll translate it into real code. So our init function for each class, get the class ID for each image, we'll append to this just piece of data, the image path, and then the class ID. Of course, for the length function, we just return self.data or length of self.data, right? Each one is one example of an image. And for the get item, we get the image and the label, and then we return the image and the label. Of course, we'd also need to sort of convert the image from a path to an actual image, but that shouldn't be too difficult. Okay, and so let's do this piece by piece. So for each class in the directory, I like to use glob as the way I traverse my files. There's, I don't know, probably 1,000 different ways to do it in Python. Feel free to do your own way. All this is going to do is sort of build an iterator of all of these paths. Okay, very quickly, we get the actual class name, and then we'll just keep track of all of the class names and convert it into an actual index instead of a name, right? This name right now will be something like, I think it's ImageNet format, and so it's like 01357, blah, blah, blah. And then somewhere else, there's some lookup table that'll make this mean, clarinet or something. Okay, and so we get the actual class ID, which isn't too hard. Just get the last piece of the path and then basically convert it into an index just by storing them in an array. Same thing for the images. We just iterate over the different files in the class directory. And then we append this all to some data array. So we append the image path and the class ID. Great. And that's our init function done. Our length function is, again, relatively simple. We just return length of self.data. So we don't really need to spell that one out. This get item function is also not very difficult. So, we get the path and the label from self.data, and then we load the image and then return the image and the label. Often, things can become a little bit more complex. So there's some important questions that we can ask ourselves. This is all of it together with some additional comments. So I'll give everyone just a moment to sort of take this in, and then we can sort of analyze this and break it down. Okay, so as a quick reminder, when we want to create some data set, we inherit this data set class. Of course, if you're doing this in Keras, you can inherit their, I think it was Keras util sequence or something like that. And we define these three functions, the init, length, and get item functions. The get item function, given some index, we return the sort of XY pair, where X is our training data, Y is our label. In the length function, we return the length of the entire data set, and the init function, we do whatever is necessary to get these to go as fast as possible. Of course, we have to think this init function is going to run once, right? And this get item function is going to run every single time we want to sort of sample an image from our data set, which is a lot more than this init function. So anything we can do in this init function to speed up this get item function is going to be pretty useful. Okay, so one question that we can ask ourselves is, let's say that my data set is, I'm lucky enough where it's small enough to fit into memory. I have enough, RAM where I can fit all of this into RAM before I sort of move it on to the GPU. And so then, we don't have to do this torch.load in the get item function, and maybe we can speed up our data loading process. How would we actually go about executing this? Any ideas? Okay, one possible option is, okay, we have this self.data, which is of course an array in memory. And so instead of storing the image path, we can just store the image data. And so basically we can just move this torch.load up here. And then instead of, some index of self.data being image path comma label, it's just image comma label, right? Of course, if we don't have system memory for this, I don't know, our computer will explode. We'll certainly receive some error when we attempt to append to this array even more, but potentially this is still a useful approach. Okay, a second question. I mentioned a couple times actually, why do we need the length function? Great question. So at the end of the day, when we're actually performing training, we'll have something like the following. Let's see if I have a better slide to draw on. Okay, I'm going to draw on this slide. We'll have something like the following. We'll say, for each epoch, for each batch in the data loader. Okay, it's very useful for this data loader to know sort of the length of the data set, because, okay, very often it needs to know how many times it needs to iterate and returning the length. And more importantly, when sort of on the back end, when each process, each one of these workers is retrieving an item from this data set, all they're really doing is saying, data set of index 5. or something, right? Let me get data set of index 5. Let me get this example and work with it. But we can't really index into this data set if we don't know the maximum index. And so that's why we need the length function, because it just tells this data loader what the maximum index is, right? So if the length is 100, we'll know that it doesn't make sense to get index 100. We can only go up to index 99. I hope that makes sense. Okay. And so, that's one easy way of preloading, but how do we add augmentations? So these augmentations pretty much necessarily have to happen in the get item function, right? Very often these augmentations are random, random rotations, random, what we call like color jitter, changing the colors a bit. If this is text, random masking. If this is, I'm trying to think of other modalities. If this is audio, pitch shifting, or, okay, I'm not sure about the other augmentations we do to audio data. But yeah, so there's many sort of things that we can do. And because they're random, it doesn't really make sense to do it ahead of time, because each time we do it, we want it to be different, right? And so, okay, how do we actually execute this? Generally, the approach is pretty simple. So we can just pass in an additional parameter here, something called like transforms. Make sure to actually save it here. So say self transforms equals transforms. And then all we have to do in this get item function is say something along the lines of image equals, okay, apologies for my mouse handwriting. I know it's pretty hard to read, but image equals self.transforms of image, right? Actually augmenting the image. And recall that this get item function is sort of being executed on each one of our workers. And so as long as our workers sort of have enough time, as long as there's not enough overhead, then this shouldn't sort of incur too much decrease in our training time, or increase in our training time, I guess, decrease in our training speed potentially. Okay, and this is really the heart of it. So let's look at a couple other examples. So very often, again, our data sets are not quite of the correct form and maybe a little bit harder to work with. So maybe we just have a folder with a ton of MP4 files. Let's say we have a data set of this form. How could we create a data loader for this? So the first question is what is one example from our data set? And okay, previously this question was easy to answer, but I think now it can become a little bit more sneaky. Is one example an entire video? Recall that a video might be a different number of frames. So this one might be 55 frames because I'm a very quick biker, but Professor Kidrotenko is a very slow cook. And so this one is 1,000 frames, right? If we want our model to be able to attend to both of these, it might be quite difficult, or maybe this is what we want, but our model architecture will certainly have to be able to handle different input sizes. So maybe an example from our data set is sort of what we'll call a clip. So if this is the 55 frames in our video, then a clip would be sort of a subset of n frames. So we'll just say this is like 10 frames or something, right? And this is a valid clip. This is a valid clip. This is a valid, oh, that one's a different length, but right? And so there's sort of many, many examples, single examples from a specific video. And so when we say what is one example from our data set, it actually might not necessarily be just one file, right? And in this case, it's really not, right? In this situation, my video would have 55 minus 10 plus 1 examples. This is the first example, and you keep sort of convolving it over, I guess. It's like a 1D convolution. And so this would give us what, 46 different examples from my data set. And then Professor Kidrotenko would have 991 different examples. Now, this raises all sorts of other interesting questions, right? Is there sort of this data imbalance now? Because, this cooking task is represented, more than 20 times more than my task. That might be true. And so maybe we want to redefine what a sort of sample is, right? Maybe a clip is not a contiguous segment of 10 frames. Maybe a clip is like 10 uniformly sampled frames across the entire thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that wasn't nearly uniform, but maybe you get the idea. And these are all, very important questions with maybe not completely clear answers. And, maybe just add one more possibility into the mix. Why not take some strided clip? So instead of every frame, we take every other frame. It's still 10 frames, but we just skip every other frame. And the idea here is now we have this larger time window. Our model might be able to perform better. Or maybe we do both, right? Maybe we want our model to be able to do this regardless of sort of the stride. These are all different options, right? And again, it's not completely clear which one is best in some specific use case, right? If all of these videos were the same length, it would be very nice just to treat each one as a single example, and then we would be done. If they're not the same length, and we do still want to process on fixed length segments, we have to start asking these sort of important questions. And of course, this example is not unique. This happens very often in audio. This happens clearly in video. Even in text, we sort of have to choose to make these cutoffs in certain places. Okay, so my next question would be, how can we represent this one example in an array? Okay, I mean, one easy way is, how do we understand that a specific clip is in a specific location? Well, I understand it as two things. First, the clip itself, so the actual path to the clip, and then second, what I'll call this offset, so the first frame, right? That's fine. What do we need to do to build this array? Well, we have to know the length of each video, right? So this clip, for example, would have, some path and the offset at 0, and then the path and the offset at, the length of the frame minus the length of our window plus 1, right? Okay, and then, so this is sort of many different examples in our data set. And when it comes to our get item function, we can sort of read the video path, slice by the index, and be done with our lives, which is nice. And so that's just one approach. There's others as well. And I think that this specifically raises other interesting questions. So the reason why we really do care about these data sets and not just these data loaders is, if we want some 10-frame window from some 1,000-frame video, very often we have to decode a large portion of this 1,000-frame video just by the nature of these MP4 files, right? And so doing some pre-processing beforehand, maybe converting these MP4 files into, individual frames potentially, or much more common is we can convert them into HDF5 format, or just H5, I think some people refer to it as. These, basically just store some n-dimensional array, and they have the benefit of being very quick to slice. And so if we need to, basically say, okay, this is the height of our image, this is the width, flipped it. Width of our image, height of our image, each cell has RGB. If we very quickly need to sort of slice out these 10 frames, it's very quick to do so. Much more quick than something like MP4 or, AVI or other video formats. I can't remember what the slowest is. I think it's like FLV or something. Yeah. So, there's a lot of sort of things we need to consider when we're building these data sets. And, it's the same process at the end of the day. We ask these questions. We say, okay, I think that it's worth it for me to spend the extra, 2 hours or so writing a quick script to convert all of these videos. But, okay, this is also not free. MP4, while it might be relatively slow to decode, not too slow, it is very small, right? It's highly compressed. And so if we then, convert it to something like NumPy, just, a raw array, it's going to be huge. It's going to be really, easily 10 times larger, probably, if not much, much more. And so we have to be careful, right? Do we have a fixed amount of storage? If we're doing these expensive augmentations, especially on videos, which can get expensive pretty quickly, is that worth our sort of storage space? Is this what we want to be spending our storage space on instead of, potentially other things, splitting it into individual images and maybe taking a little bit of a hit of overhead of combining them back, but maybe it's worth it. Again, these all sort of come down to the individual data sets. Also, what machine you're running on, right? How many cores do you have, and what's the resolution of your data? One project I worked on, we had extremely long video sequences of 14 hours plus. And also the images were 4,000 pixels by 4,000 pixels. And this created a variety of different interesting problems because it's really slow to move this data around, right? We have to store it in binary format, and we have this fancy data set that finds the perfect place to begin reading if you want like a specific frame, and all this other stuff, quantizing these bits so that it's much more compressed, because otherwise it takes up a stupid amount of space. These are all sort of valuable questions to ask ourselves. Okay, we'll look at one more example, just because it's pretty common, which is, okay, we just have sort of file names that are unique, but not necessarily very useful. So in this previous example, they were pretty useful, right? We can get the label by, splitting on a period and splitting on an underscore, and then extracting this and, I don't know, using some array or some lookup table to convert that into some class index, right? That one's not too hard. In this situation, there's absolutely no information in the file name, but okay, let's say there's usually some CSV that contains some mapping to it. Hopefully, this also should not be too hard. So what is one example from our data set? Again, sort of up to us. We'll just say for ease, all of these audio samples are the exact same length, or maybe our model is supportive of different length audio samples, right? Some recurrent neural network or some attention-based network that has some sequence length that is long enough. So, okay, what is one example? One example is sort of one row. How can we represent these in an array? By reading this CSV and storing it in an array, basically, right? What do we need to do to build this? Read the CSV. That's pretty much it, right? And then, of course, we still have to maybe worry about these data augmentations and things. Okay, one other thing that I just want to sort of briefly add, there is a ton of open source libraries and packages out there that make loading data fast. PyTorch and TensorFlow's data loaders, these are all PyTorch examples. I mostly work in PyTorch, so I'm actually a little bit less familiar with the TensorFlow ones, but I know that there is copious amounts. There's a ton out there that speed it up in a variety of different ways and are very easy to use. And so, if you find yourself, really, really needing performance, I think that, if you only need a little bit of performance, just do it yourself, tune your hyperparameters and go from there. If you, care about performance, but don't want to spend a huge amount of time on it, I really highly recommend, using these packages. A lot of these are supported by HAL, not all of them yet, like FFCV, Fast Forward Computer Vision, I think it stands for. Just got released, and so I don't think it supports the HAL architecture yet. But like, okay, PyTorch Lightning is amazing. Cornea is really great. PyTorch 3D is really great. This Detectron 2 framework that Facebook released is just a really awesome framework to work inside of. This has a ton of useful and fast image augmentations. I think Torchbearer is a part of PyTorch Lightning now, which is nice. I can't remember what this one is, frankly. But these are, super useful, super nice. And, it allows you to just leverage other people's code to do this acceleration. Now, I will say, at the end of the day, your data set and your computer better than these people. And so it's likely that if you spend enough time, you can probably get results that are faster than these people. And so if you really, really care about performance, to the point of, saving your images as binary files and doing all this, crazy stuff, then it's probably more worth it to start to look inward again and start to develop these accelerations yourself. Okay, and then at that point, we're worrying about other things like distributed training. But okay, so now we can sort of look at this live demo. I won't spend too much time on this. Basically, the rest of this is free for Q&A. So thank you all so much for coming. If you want to head out, if you want to continue to sort of discuss data loaders together, I have this collab up as well. Basically, I've formatted it in such a way where it downloads some data sets for you and allows you to sort of create your own data sets and test how fast it'll run, without having to write all this boring boilerplate code. And so I encourage you, if y'all do want some practice, try giving this a shot. I've written a lot of the sort of framework for you, and so it should be maybe not too difficult. And then there is a harder sort of example at the end with this video case. And then, of course, I've also provided you with solutions in each. I do not claim that my solutions are good or definitely not perfect or even good, but they are correct. They do work, at least for what I was imagining. So hopefully that those can be a little bit helpful. But yeah, that's pretty much it. If any of you have any questions, please let me know. But thank you so much. And have a wonderful, I guess, rest of your day.
Well, thank you, William. Thank you very much for this valuable tutorial. So yeah, if anybody has any questions, please ask.
Oh, and I will mention that the example that I give is using PyTorch again. Okay, that's just because I know PyTorch much better than TensorFlow. So if you're a TensorFlow user, I guess this is like the Vim versus Emacs discussion, right? Yeah. Okay. Will the recordings? I think so. Yes.
Yeah, they will be posted on our website, ai.ncsa.
Is it bad that, okay, I use Vim most of the time, but every once in a while I'll use Nano. And I think that that's truly just frowned upon in the Vim versus Emacs discussion. I don't know. It's easy. Oh, and then one other thing I want to add for those of you who are still here is this example that I give also has a little actually custom augmentation example. So it's not too uncommon that we have to build our own image augmentation functions. This has one that's pretty simple. PyTorch has this random resized crop for images. This one is the random resized crop for videos. And so it just makes sure that we're cropping consistently across the video. 99.9% of the code in that is from the PyTorch source, and 1% of it is adjustments by me. But maybe it's still useful to know that it's quite easy actually to adjust these to work how we want them to work. And to build our custom transformations. Other sort of things that I'll mention in passing, when we do have some data set and we don't maybe have some pre-made train test split like this, it's very useful to maybe define this once and then forget about it, or not forget about it, but define it once and then just stick to it instead of, having it, define some random number that you always stick to, or just save two CSV files, one for train, one for test that has the labels for those, just to maintain consistency. I've had some real pain in the past of every once in a while just kind of getting a bad sample from a data set for a train test split, or for getting some train test split and not being able to reproduce good results, and then I'm sad and I don't know if my algorithm was good or if I just got lucky, and yeah, things like this. And then, yeah, I think that's pretty much it. At the end of the day, just, test some different values. I think it's very quick that you get a good sense, a good intuition for what's going to be the slowest part. And then you know how to change it, hopefully quickly. Okay. I guess for the rest of the time, I'll pull up the data loader or the tutorial on my own machine here, and we can sort of slowly walk through it together. Can you all see?
Yep.
Awesome. Okay, so I'll just connect to some runtime. I give maybe no guarantees of this code being perfect, but it worked for me when I ran it. So that's what I'll say. I do recommend keeping this to false. This was just me troubleshooting around for things. And then we will have to restart the runtime once after this. So. If anyone needs the link to this, it's in chat. Post it again if you need me to. Okay, so let's start to sort of walk through this together. So these first couple cells just download this data set in a way that will be easy for us to work with. And then our first problem here is just creating a basic data loader for our data set. We want to return, we won't worry about augmentations or transforms yet. And we do want to return sort of our data, right? Given some root. And so I'll wait just a moment for this to download. if I recall, it's the same sort of format that we saw previously, but I'll have to double check. I don't want to start doing something and then have to change it. Oh yeah, okay, it wasn't. Okay, so this is still unzipping and things. The format of this first data set, this ImageNet Mini, or Mini ImageNet, I guess, is, I believe, just like so. So we have some folder called data, and then within this folder, we have many, many files. Each one sort of has this format of unique ID, class, ID, and then some ID within the class, if that makes sense. And then I can't remember if it's probably JPEG. And so, okay, let's ask ourselves these questions. What is one example? A single image. I can't remember the other two questions right now. Okay, how can we actually build these into an array? Just by iterating over the files, right? And then, okay, that's actually relatively straightforward. So this one we'll do first. Again, I like to use glob, so I can say self.files is glob.glob. And we'll take a quick peek inside of this. We can see all of the files. So it's, okay, all of the files in root. And that's pretty much it, done. Okay, what is the length of our data set? Self.files, of course. Okay, and then in our get item function, we need to do, okay, a couple things. Load the image, process the label, and then return the image and the label. We'll load the image first. So to load the image, we first need to get the path, which we can just index into self.files. Next, we'll actually load the image. Just using the Torch Vision read image. Again, there's probably a trillion different ways to read images. Another good way is using PIL, or Python image library. PIL also has, I think it's relatively fast, and it also has some very useful augmentations, which can be nice. Okay, let's also get this class ID. So recall that path is going to be, some path to the file, and then at the end it'll be something like this. I'm just going to steal an example from the right. Okay, so this, for example, is image number 100. That is class number 16. Okay, and so it should be relatively, hopefully not too difficult. Some string manipulation will say that the class index is equal to path.split. And we'll just split on these underscores. Maybe there's some risk of underscores being in this initial path, but I know for a fact that there aren't any. So maybe it's not too difficult. Okay, underscores of -1 will be this, -2 will be that. And that's the class ID. And then, of course, we'll want to convert it to an int, or maybe even a torch tensor. And life is good. Okay, so we'll see if this works. No promises, but fingers are crossed. Oh, okay, this is still running up here. Yeah, it's downloading the video data set. I'm gonna not let it download the video data set. Okay, run this. We'll see if it works. Yay, it works. Okay, and so in this example, it looks like, okay, the colors are a little bit weird because of this disagreement between matplotlib liking images in a certain way and PyTorch, but it seems like these are shoes. I can't remember what class this is, but okay, they're at least labeled as the same class. Hopefully I didn't mess up the way I was pulling my classes. Maybe I did. Let's check. So I'll just add a little print statement here. And we'll see if I messed up doing the classes. So this one is class number 40. This one is class number 27. So, okay, we can see I already found a bug in finding these classes. So let's figure out where this went wrong. Oh, okay. I think where this went wrong is previously I was expecting a one hot encoding, and now I'm expecting not a one hot encoding. Okay, I think it'll be, okay, well, it's pretty easy to convert between the two. If we have some index, we can just say self dot num classes 64, and then do something like torch.i class index. So this is just the identity function. Of course, if we index, the 0th row in the identity function, we get 10000. The next one is 01000, etc. And so, okay, if we just index the nth one, then we'll get the one hot encoding for that class. Okay, now it should not yell at me. Oh, it yelled at me. Yeah, this time I'm not sure why it's yelling at me. It just, what did I mess up here? Oh, it doesn't like this torch.i. Oh, okay. Let's just do this out here. Third time's the charm. Okay, it's a little bit strange. I mean, this is functionally the same thing I have in the solution. And the solution works, so we're just going to go with the solution. Okay, and now we have two examples of shoes, right? We can pick another example. We'll pick 881. And now we have two examples of coyotes of some sort, maybe some sort of fox. Okay. And of course, there's a lot of things we can play with after this. So the batch size, the number of workers, the prefetch factor, and then here's just a quick little training script. We don't really care too much about accuracy, so maybe don't worry too much about it. But tuning these is maybe valuable, right? Remember, we want to basically max out our batch size. Number of workers should be the number of cores as a good rule of thumb. Prefetch factor, sometimes you just have to play with a little bit, things like this. I will mention occasionally I found better performance. Okay, so sometimes it's like common practice to, let's say I have 8 cores, I'll say number of workers is 8, and then prefetch factor is 1 or 2, some low number. I've also found pretty good performance with like a very low number of workers and a very high prefetch factor, but I don't know if that's very reproducible. It happened once. Okay, okay, let's add augmentations to our previous example. Since we used the solution, I'll just yoink. Okay. And so we want to add augmentations. Okay, it's pretty easy to add augmentations. We can just do something like this. So add transforms as a parameter here. Make sure we're keeping track of it so that we can access it in the getItem function. And then once we have our image, we can say image equals self.transforms of image. Looks good. Let's see if it works. Okay, so it's beginning training. I'm not going to let it continue because I'm not going to tune all of this. But okay, again, it's good practice too, right? Tune these things, larger batch size, things like this. Okay, and then our last example, which is a little bit more advanced, we have some video, right? So we've downloaded some video data set. Oh, I should probably run that cell that actually finished downloads. Finish downloading the video data set. Okay. Okay, hopefully that'll finish. Okay, we have some video data set, and we run into this issue once again, which is like we have this idea of valid clips within a frame. But how would we actually go about, executing this? I think this, example of clips within a frame is bordering, some of the more difficult data set examples you'll have to do, right? Sometimes if you're doing crazy file formats and things, they can get a little bit messy, but hopefully it shouldn't be too hard. So, okay, first of all, we probably want to be able to parameterize this number of windows, right? Or the number of window frames. So we know that we can at least do that. And okay, we'll store the paths just in case we need them later. Okay, and now we can sort of, okay, well, maybe we even add transforms in here too. Okay, so what is one example from our data set? Well, it's one of these clips. How can we determine how many clips a single video has? Well, it's based on the total number of frames in a video, right? This n minus m plus 1. I think I swapped my terminology there, but it should be fine. So first thing we need to do is iterate over each of our videos. So for video path in glob.glob, the root path, any file within it. We'll read the video. If you get an error on this video data part, then you need to go back up and install PyAV and restart your runtime. Not all. Okay. Where were we? Above this. Shrink that. Okay, so we've at least read our video now. From the docs. So read video PyTorch. Just from the documentation for this read video, this returns a tuple. The first thing is the video frames. The second thing is the audio. And then the third thing is the metadata. In this situation, we'll only care about the video frames, so we can just index into it and be done. And then the shape of this is frames, height, width, channels. And of course, the one that we really care about is the number of frames here, right? So for, we'll just say index I in range 0 to frames minus self.window plus 1. We can store this example or remember that this is a single example. So we'll just say self.clips, self.clips.append. What do we need? Well, we need the path to the video, which is video path. We need the index or the offset, right, where this clip begins. And then, of course, we also need the label. Okay, this label in this case, I believe it's, oh yeah, okay, here it is. So these file formats, it hasn't finished unzipping yet, so sad. Okay, so this will go for a while, but this file format is, if I recall, in the form, whoops, where'd we go? In the form action underscore person underscore trial dot AVI. And of course we want action, right? And so we can say the file name is the video path dot split on the slash. So now we only have this part dot split on the underscore. So now we have an array of action person trial. Get the first one. And then we can just say class index is int fname. Though, okay, these actions are always of the form like A21 or A1 or something. And so we say int fname, except for the first character. And then they are 1 indexed instead of 0 indexed. So we subtract 1. Okay, what's the length of this? Just length of self.clips. How do we do a get item? Well, path, offset, class index is self.clips of index. Let's first worry about reading this video. So video data is, again, torchvision.io read video of path and we only care about the video data. And not only do we only care about the video data, but we only care about our specific slice. So we can say begin at offset and go until offset plus self.window. Recall that the shape of this video is frames, height, width, channel. Of course, PyTorch likes it channel first, so we'll change it to channel, frames, height, width. Video data equals video data dot permute. We want the new first axis to be what was the third axis, the new second axis to be what was the 0th, then the first and the second. Perform any transformations. And then return. Great. Hopefully this works. We will certainly see. Okay, so we will pass in the path, which is still not done. Oh, I see what happened here. Okay, I'm not going to worry too much about this. This will work on yours if you don't keyboard interrupt it like I did. And then I know that this should work. And if it doesn't work, we can just use the example, which should be very similar. But okay, this is functional. It is slow. It's super slow. So if you did try to train on this, I think it would take something like 6 hours. But you know, such is the nature, right? We're using MP4s. We talked that might be slow, especially for these long videos. If we wanted to accelerate it even more, you know, there's a couple options. Potentially, you know, return multiple clips from the same video. You know, does this maybe lead to some weird oversampling? Potentially, but does it also maybe drastically speed up our training? I would say yes. And so maybe the sort of cost is less than the benefit. And so, you know, we can select not only a single offset from this, but like select 5 or 10 different clips from the same video. And train on all 10 of those at once. This means we only have to decode the video once. Now, we still have to move the data over, which would be slow, but okay, you know, nothing is for free. Again, if we had enough memory, which is super unlikely in the case of a lot of videos, we could store all of these into RAM. But again, that's pretty unlikely. You know, little things though, like performing this transformation, which is a cropping and a resizing from, you know, something like 640 by 640 resolution to, I think I said 224 by 224. You know, making sure that if we did try to store in memory, that we do this transformation beforehand, not only saves us time, you know, when we're sort of iterating through our data set, but also saves us, you know, 4 times the memory, or maybe even more, 9 times the memory. That's about a third. So, okay, you know, there's a lot of maybe good benefits that we can have by changing these things. And then, okay, there's other things as well, right? If we adjust this frames per clip, our data set actually grows and shrinks, which might be interesting, a good thing or a bad thing. We haven't really dealt with this issue of oversampling longer videos. You know, if you were going to do so, I think you do so in the init function, right? Say you want 10 clips from each video, and you know, basically instead of this, we just change this for loop to say like pick 10 random offsets within the video, and that'll be our 10 clips from that video. Okay, I hope this all makes sense. I hope that these were some useful examples with a couple different modalities. If any of you have any questions, feel free to reach out. I'm more than happy to sort of answer any or ask now. But if not, I think that's everything from me. Thank you all so much for your time.
Okay, but sounds good. Yeah, thank you very much. So great. Yeah, I'll see you later.
Yeah, tomorrow morning. See you soon.
Tomorrow morning. Right, yeah. Okay, bye.